1.2.P10. If A is in n by n matrix in real number, and if n is odd, show that matrix A has at least one real eigenvalue. So first, let Pt is equal to determinant A minus Ti. So this is the characteristic of a polynomial of matrix A. So, and then eigenvector is defined as this formula. Matrix A vector is equal to lambda vector V. In n by n matrix A, vector V is called by eigenvector, and in this condition we can call this lambda as an eigenvalue, and vector V must not be a zero vector. So if we relocate this formula, we can write it as A minus lambda I and vector V is equal to 0. If A minus lambda I is invertible, vector V has a root of 0, but it violates the rule to be an eigenvector. So to prove A minus lambda I is not invertible, we should calculate the determinant. So if determinant A minus lambda I is equal to 0, we can say there's an eigenvector. So we are now able to understand the characteristic of polynomial. In this problem, n is odd number. So the leading term is minus t square n according to the matrix characteristic. Then we can rewrite our formula like this. Pt is minus t square n plus and some other row terms. So if t is increased, pt becomes to be minus infinity. Likewise, if t is decreased, pt becomes to be plus infinity. So we can write like this. So, and in this condition, we can use intermediate value theorem. So, in intermediate value theorem, so in function fx, if the function has so in this polynomial, there is a two root. So in our problem, we have to show there is at least one real eigenvalue. This means we have to prove there is one root, at least one root. So our result expands from minus infinity to plus infinity. So there must be at least one root according to this intermediate value theorem. So this root, once we have this kind of formula, then we can say Pt has at least one root. That means Pt we define the Pt as a determinant of A minus Ti. So it has at least one root. That means it has one eigenvalue. So this problem can be solved like this.